The broadcast is now starting. All attendees are in listen-only mode.
Hi, everybody. This is Viviane Silva from the OER Weather Program Office, and welcome to the Week 3 to 4 S2S webinar series. And today we are going to have two presentations on machine learning. The first presentation is going to be by Eric Maloney from CSU. He's going to be talking about improving S2S precipitation forecast in UFS through tropical nudging and explainable machine learning, and will be followed by Nachiketa Acharya from Penn State. He's going to be talking about predicting Indian Monsoon onset in S2S scale, a machine learning framework. And so for those in the audience, this is our website of the webinar website. So if you would like to subscribe and receive information about the webinars, and you can just go to our website and click here and subscribe. Also, if you have interest in speaking and making a presentation to this webinar, you can just fill out a Google form that we have. And also the previous webinar, they are all here on the page in case if you have interest in see some of the presentations and also the discussions. So one thing else, before we start, I want to mention that one thing that we share with you all, we have this discussion document. This is where we ask that you can put your question there so we can record all the questions. And if the presenter has time during when he finishes his presentation to address some of the questions, so we are going to spend some time addressing the questions, but if not, all the questions will be here. We are going to make sure that you are going to get an answer for the questions. And so said that, I am just going to pass the word to Eric. So I just need to make him a presenter. Just a minute. Eric, you have the floor.
Okay, so you can see my screen. Let me put it in presentation mode here. It looks okay?
Yes, sounds good.
Okay, great. So let's see here. I'm going to be talking here about S2S prediction of precipitation in UFS. And I'm going to spend most of the time of this presentation talking about some tropical nudging experiments that we've been collaborating with folks at NOAA Esrael on doing. And assuming we have some time, I'm going to talk about extension of this work to use of explainable machine learning to try to look at West Coast precipitation biases and errors. So again, this is work that I've been doing with Elizabeth Barnes and Wei-Ting Shou, who actually did most of the work that I'm going to show here at Colorado State University. Wei-Ting is one of our students. And Juliana Diaz, Stefan Tulik, and George Kalatis have been collaborators at NOAA Esrael. And they've been the masterminds behind the tropical nudging experiments that we are going to show later. Okay, so first of all, the phenomenon that is going to be the focus of this talk is the MaddenJulian Oscillation. So this is the dominant mode of tropical intraseasonal variability, and it's associated, again, as you might know, with a blow-up of precipitation over the Indian Ocean that moves towards the east with time and ends up over the Western Pacific. Very important phenomenon for thinking about not only subseasonal precipitation prediction in the tropics, but also through teleconnections, as we're going to talk about here, subseasonal prediction in mid-latitudes as well. This is a great figure here that was developed by the S2S Prediction Task Force under MAP, showing all of the various processes on the subseasonal that are responsible for good predictions over North America and other places. The MJO is the core of this, and so, for example, the MJO has impacts on tropical cyclones in the Eastern Pacific and Caribbean Sea. That is something I worked on as a graduate student, actually, 20 plus years ago, but you could actually use the MJO to think about tropical cyclone prediction. We're not going to do that today. The focus of this talk is going to be thinking about prediction over North America, in particular, prediction of West Coast precipitation over North America. And to study that, it's really teleconnections through the mid-latitudes associated with stationary Rossby waves that are important for thinking about that particular process. So why is the MJO important for West Coast precipitation? Well, it modulates things like atmospheric rivers. And so there's been a lot of great work by the variety of folks that you see up here and others looking at atmospheric rivers along the West Coast, and also thinking about MJO modulation of atmospheric rivers along the West Coast. And so Libby and I did some work with one of our former students, Brian Mundhank, back a few years ago, where we were looking at the implication of the MJO for West Coast atmospheric river activity. And so Brian developed a detection algorithm for West Coast and global atmospheric rivers that we actually used in this work. So one of the things that we did is that we looked at the modulation of atmospheric river activity over not only places like California, but also places like British Columbia, and parsed out the modulation of atmospheric river activity by MJO phase and also QBO phase. And so these two plots show what the anomalous atmospheric river activity looks like along the US West Coast during the westerly phase of the QBO. And by westerly phase, this is the QBO defined at 50 millibars. So MJO phase is on one axis here, going through phases 1 through 8. You could think about these phases as being a particular location of tropical precipitation associated with the MJO in the tropical belt. So 1 is when the MJO is over the Indian Ocean, and 5 and 6 is maybe when the MJO center is over the Western Pacific. Also shown on this plot are the number of days after a given MJO phase condition. So you can see here that there's a substantial modulation of atmospheric river activity along the US West Coast. So for example, phases 1 through 3 here are associated with an enhancement of atmospheric river activity over California. And maybe not coincidentally, the most recent atmospheric river activity that we saw was kind of in MJO phases 1 through 2, barely meeting kind of the threshold. And the QBO is in a westerly or very weakly westerly phase at 50 millibars. So what happened recently over California kind of fits this plot here. Okay, so why do certain MJO phases have strong teleconnections? We're going to talk a little bit about that now. This is an MJO phase diagram, again, from phases 1 through 8. And on this plot are time lags, lags 5 through 9 days, 10 through 14 days, 15 through 19 days after these particular MJO phases. And so you could see here that MJO phases 2 and 3, and also 6 and 7 tend to be associated with very strong teleconnections to places like the North Pacific and the Aleutian Low region. Other phases don't have very strong teleconnections. So we're actually going to think about this a little bit later on when we do these tropical nudging experiments to think about why tropical nudging tends to improve certain phases of the tropics relative to other phases preferentially. So why do certain phases tend to have stronger teleconnections? We thought a lot about that with one of my former graduate students, Stephanie Henderson, and also one of our other former graduate students, Kai-Chi Seng, where certain configurations of MJO precipitation in the tropics tend to be associated with very robust responses. One of those phases, for example, is MJO phase 3. And MJO phase 3 tends to be associated with a dipole-like precipitation pattern with the MJO in the tropics. And so it tends to be associated with enhanced precipitation over the Indian Ocean and suppressed precipitation over the Western Pacific. this sort of dipole type pattern in precipitation anomalies produces a dipole-like pattern in Rossby wave source across the North Pacific jet, as you can see on these right-hand panels here. And a dipole-like pattern like this tends to produce a very robust North Pacific teleconnection pattern because there's constructive interference between Rossby waves launched in the region over Asia and the region over the east side of the Pacific jet. So Rossby waves launched in these two different regions tend to constructively interfere with one another to produce a very strong teleconnection pattern, PNA-like pattern that you could actually see here. Other phases do not have this very ideal configuration, so that's basically why only certain phases tend to produce robust patterns. Okay, so what is the implication of this for model simulations of the MJO? It's been known for quite a while, and it's still the case, that climate models and weather forecasting models tend to struggle with their MJO simulations. There's a lot of reasons for this. One big reason is the parameterization of deep convection in weather forecasting and climate models for producing a poor MJO. For example, many climate models are not sensitive enough to environmental moisture as far as launching deep convection. So if you make convection more sensitive to environmental moisture, it tends to produce a better MJO. But regardless, a lot of MJO biases in models. And so what are the implications of this for Western United States forecast errors? And so that's what we're going to look at next. So Juliana Diaz and collaborators at NOAA Esrael actually started looking at this issue in this particular paper. And so what they did in this particular paper is that they looked at the implications of tropical precipitation, wind, and other biases for forecast errors in the Northern Hemisphere during boreal winter. So what they did is they looked at a version of the UFS, GFS version 15.1.1, and they looked at two different sets of runs. So one set of runs that they looked at was a set of free hindcasts during 1999 to 2018. Again, this is during boreal winter. And they compared it to another set of hindcasts in which the tropics were nudged to reanalysis. And so they looked at a variety of different variables in terms of nudging. They looked at a variety of different widths of the tropics that were nudged. The results that I'm going to show here are nudging experiments where they nudge wind, temperature, humidity, and pressure, and nudge between 30 north and 30 south, such that there's perfect nudging between 10 north and 10 south, and that tapers off to 30 degrees towards either pole. So again, they also looked at other types of nudging, but the experiments that I'm going to show are nudging from 30 north to 30 south in these variables that you actually see here. So Juliana et al. Showed that, first of all, some plots looking at mean absolute error for the entire, hemispheres when you actually, do these nudging experiments. So the first plot, that set of plots that is shown on here, are rows that show the hindcasts without any nudging done. And week 1, week 2, week 3, week 4, these are different weeks into the hindcast. And what's shown here are mean absolute errors for 500 millibar height. And you could see here, not surprisingly, that without nudging, 500 millibar height errors grow with time. So by week 4, you could see that there's some substantial errors across much of the mid-latitude regions. With nudging, you could see this set of plots here. So this set of plots here shows the percent improvement in mean absolute error if you apply tropical nudging in the model. So one notable feature that I want to show here is that across most of the extratropics, the forecasts have gotten better. And so the mean absolute error has decreased. But you can see that there are preferential decreases in some regions of the extratropics relative to others. And so one region that I want to point out here is this region in the North Pacific and near the west coast of the United States, where there's preferentially larger decreases rather, in mean absolute error. And so that is the region that I'm going to focus on during the rest of this talk. And there's also a region where the MJO produces very notable teleconnections. Okay, so let's zoom in on this region here. So now what I'm going to show is a extension of the analysis that Juliana et al. Did that is led by one of our students, Wei-Ting Shou, here at Colorado State University. And what Wei-Ting is looking at specifically are processes associated with improvements in West Coast US precipitation. So very similar, first of all, to what Juliana showed. This is a plot of the mean absolute error distribution across hindcasts. The free hindcasts are shown here in blue, and the nudge hindcasts are shown here in red. And this is the distribution of mean absolute error across all hindcasts in these two different experiments. What you can see here, not surprisingly maybe, is that when you nudge the tropics, the distribution shifts to the left. And that indicates that if you constrain the tropics, winds, humidity, pressure, that produces better West Coast precipitation forecasts, which is consistent with the plot that Juliana showed before. So again, a consistency check. And so maybe something I didn't mention is that this is at 3 to 4 week leads into the forecast. And so that's very, very important. It turns out that the improvements in West Coast precipitation tend to emerge later in the forecast period. So this is a plot here, and unfortunately I have a GoToWebinar control panel stuck on top of this that I can't get rid of. But what's shown here is the distribution of mean absolute error improvement by forecast week. And what I want to point out here is that the West Coast precipitation forecasts really start to improve by weeks 3 and 4 into the forecast. Earlier weeks, not quite as much. And so this suggests that processes on S2S timescales are really the processes that are most important for engendering this improvement in West Coast precipitation. So maybe not surprising, but that's borne out by this distribution of mean absolute error improvement by week. Okay, and further, there's only certain states of the tropics and mid-latitudes that seem to be associated with very strong improvements. And so to look at this, we actually did a k-means cluster analysis of precipitation and zonal wind anomalies from the tropics into higher latitudes of the Northern Hemisphere, and did an analysis of 8 states. And this plot here shows that one of the clusters really stands out in terms of its mean absolute error improvement relative to the rest of the distribution. So the distribution of all of the experiments is shown in this dashed gray line here. And one particular cluster really pops out as far as producing the greatest mean absolute error reductions along the US West Coast, and this cluster that we call cluster number 4 here, I think, if I could actually see it, behind the panel. And so we're going to look at what the state looks like in the next slides. So one initial state, again, produces the greatest forecast improvement at 3 to 4 weeks. I want to show you what this state actually looks like. So this is Z500 on the left side and precipitation anomalies on the right side. You can see that this state is associated with an initial anomalously deep Aleutian low and a precipitation distribution that looks like this, with anomalous enhanced convection in the Indian Ocean, anomalous enhanced convection near the dateline, and suppression of convection over the maritime continent. This state is very strongly biased towards MJO phases 8 and 1, and non-El Nino states, if you look at these measures of climate indices that you can see here on the upper right. So MJO's phases 1 through 8 and non-cold ENSO events are, what this looks like. So if you look at a composite of precipitation at different weeks after the forecast initialization in this initial state, the free hindcast without any nudging look like this. And so the free hindcast look like an Aleutian low that continues on with similar strength out into the future. And this is associated with an enhancement of West Coast precipitation. Now, how does nudging improve this? And so I'm going to show that in this next set of panels. So the free run has an Aleutian low that keeps persisting. And with nudging, it actually looks like this. So nudging tends to weaken the Aleutian low with time, and as a result, weaken West Coast precipitation forecasts, precipitation composites. And this looks like what you see in era 5 as well, right here. So with nudging, you get a much better representation of the Aleutian low than you do in the free hindcast. Now, you could also look at these MJO phase composites, and you could see that as time goes on, the MJO phase evolves. So it starts in 1 through 8, but then it eventually evolves to look more like 3, 4, and 5 with time into the hindcast. So it seems like the evolution of the MJO might actually be important for producing this Aleutian low. And we actually looked at precipitation anomalies in the model along the equator in the equatorial Pacific, and it indeed does seem like that is the case. So what we have here is equatorial precipitation. So longitude is on the x-axis, forecast lead in days is on the y-axis. So we're starting at the initialization here and going to day 21. The free hindcast show, again, the suppression of precipitation in the maritime continent, enhancement of the precipitation near the dateline, and also an enhancement to a weaker extent over the Indian Ocean. And this just tends to persist in time, kind of locking in this continuous forcing of the extratropics that supports an enhanced Aleutian low. With nudging, things change. And so we actually see with nudging, you actually get a decrease in precipitation here after a certain point in the forecast out, like 2 weeks into the forecast. And you also get a sense here that there's some propagation of this suppression of precipitation anomalies from the Indian Ocean into the maritime continent and Western Pacific. So what's going on here is that with nudging, you're able to better simulate the eastward propagation of the MJO into the maritime continent, and you're killing off this precipitation anomaly in the maritime continent that is supporting the Aleutian low. So as a result, with a better MJO and a better simulation of the tropics, you can get a better simulation of the Aleutian low because of the teleconnection to the tropics as a result. So demonstrates the importance of getting a good MJO in your forecast model for producing great West Coast precipitation forecasts. All right, looks like I'm running out of time here. So let me just give some conclusions and briefly talk about some of the machine learning stuff that we want to do in the future. So conclusions: tropical heating on various time and space scales initiates teleconnections to the extratropics. Given the slowly evolving nature of the MJO, we could actually exploit knowledge of this phenomenon for mid-latitude S2S weather prediction. And I think our nudging results have shown that forecasting models need to reproduce the tropics, in particular the MJO, accurately for getting good Western United States weather predictions. And we show this with these nudging experiments, and the nudging experiments indicate that there are certain states that are optimal for producing better precipitation forecasts with nudging. And in this set of experiments, it tends to be states with a strong early MJO phase, like in the Indian Ocean, and non-cold ENSO periods. So just to wrap up, where are we going with this? So one of our next steps here is to refine and use explainable artificial intelligence methods to identify in a bit more detail the state-dependent UFS biases and errors in tropical, extratropical teleconnections. And particularly, we want to look at the implications of this on North American precipitation forecasts. So one of my collaborators on this, Elizabeth Barnes, has used similar techniques in order to predict weather patterns over the North Atlantic. So for example, they came up with heat maps that were developed using a neural network to predict Z500 anomalies over the North Atlantic, and they showed that certain regions of the Pacific, particularly the Western Pacific Warm Pool and an area near Hawaii, were very important for producing good predictions over the North Atlantic. So we want to do something similar here, where we key in on West Coast forecast errors and use controlled abstention networks to generate heat maps of where the errors are more sensitive to regions of the Indian Ocean and Western Pacific. The other thing that we want to do is build off of these state-dependent errors that we developed to diagnose the physical processes that lead to these biases. And so we're interested in using weak temperature gradient process-oriented diagnostics of the tropical moisture budget to tease out why UFS might not be producing great MJO simulations and why, from a physical standpoint, it's not producing good MJO simulations. And we also have some other ideas to use AI correction methods to improve US precipitation forecasts, using bias corrections that we also are thinking about. So I guess that's all I have. And if you have any questions, feel free to ask them, and thank you for your attention.
Thank you, Eric. Excellent presentation. So yeah, I believe there is one question for you in the discussion forum. If you want to open, we have in the chat the link if you want to open and just check. Okay.
Okay. Looks like a question from Nat. Is there any quantification of how much of the tropical nudging represents possible correction of model error versus unpredictable noise? That is something that we haven't really thought too much about. Nat, I guess my answer to you there is, maybe I'll think a little bit about that offline, and if anything, comes to me, I'll let you know. But we haven't explicitly looked at that in this particular analysis here. But thanks for the question. But I'll think about that a little bit more, and maybe type that in if I can come up with any epiphanies offline.
Okay, thank you, Eric. And for everyone, if you still have questions, you can just feel free to type your question, and then we are going to, Eric is going to be here and he might be able to answer some of the questions. So thank you. And with that, I'm going to pass the word to Nachiketa Acharya, and I'm going, just a minute, I'll need to make him a presenter. So. Okay.
Can you hear me?
Yeah, just put in the presentation mode.
Yeah.
And then you can start.
Let me know if you see the presentation mode.
Yes, looks good. You can start. Thank you.
Okay. Thank you, the organizer, for this call. And yeah, so today I'm going to talk about something different, which Eric told over something US. I'm talking about something on India. And as you see the title, the Indian Monsoon onset. So it's very important phenomena in terms of dynamics and in terms of the application. So let's talk about, but before that, I want to acknowledge to some of my colleagues. In fact, this work is like part of the summer intern of one of the student who is actually a second-year computer science student. And also I want to acknowledge the scientists who are actually working in the operational forecast of Indian monsoon onset from Indian Meteorological Department. And also my colleague from Colombia, who is helping me to develop this whole machine learning approach. So to start with, just a little bit of rainfall distribution over India. You can see from this bar diagram that we have a seasonality, which is from June to September, and we call it monsoon rainfall. And especially it's look like very interesting. You don't see like everywhere you can get rain, but most of the land over India get rain, but it's very highly variable. So it's not a very easy time series to predict, just a total rainfall. So it's tough, but in terms of definition of monsoon, it's not only the rainfall, it's actually the reversal of wind over the tropics. So if you look at December to January, the winds blow from the northeastern side, but from June to July, it stays. So it has lots of dynamics behind that, and there's lots of study. I'm not going to talk about the monsoon here, but just let know like what are the drivers which helped to start the monsoon, because that's the important and key for this research, that we are not talking about only the total rainfall. We're talking about the trigger which make the monsoon start, monsoon rainfall start, and we try to capture those variable to predict. A little bit of the definition. So it's interesting, like Indian Met Department is a very advanced Met Department, and they have a very a good definition for the monsoon onset. But if you look their website, it's written that onset monsoon over Kerala. So Kerala is one of the southern state, and the monsoonal wind actually enter first in this state in India. So that's what they thought, like this is the first advancement of the monsoon. So they have more interest on making the definition of the monsoon onset over the Indian landmass. And this is like a long like research since 60s, and people are doing lots of research to try to understand that how to make a definition. It should not be only based on the rainfall, it should also based on the wind field, outgoing flying radiation, and different kind of thing. So based on those research, so Indian Met Department defined the definition. But interesting thing is like they keep on changing their definition based on the last 30 years. And interestingly, last year they published a paper which is based on the new definition of monsoon onset. And based on that definition, they're also monitoring the monsoon onset over the other part of India. So this is an example of this year, 2021 monsoon. So those red line, if you look, these are the normal or climatological onset, but the blue line is actually the real monitoring. So why I'm showing this thing, the interesting thing is, although they have a climatological onset dates, but not every year the onset dates are same. So that means there's a variability over the onset dates, and which make a real trouble for the decision makers, especially for the agriculture. So as I mentioned, that prediction is very important. Although we know this, especially for the map, we can see the climatological onset date of Kerala is 1st June, but it has like a standard deviation, few days, around 4 or 5. But it's very crucial to know this information in terms of the agriculture strategy, because it influences the land preparation, showing, transplantation, and other things. It's very important. So what Indian Met Department do, they started a prediction system since 2005. And so it looked like every like second week of May, it might be 14, it might be 10, depending on the calendar, they kind of published a press release about the monsoon onset since 2005. And they're using some method, which is a very linear, called principal component regression. I'll come on that method in next slide, but this is like on that operational mode, how it looks. So in 2 weeks advance, they make this prediction, and kind of putting in a press and media so people can understand, like, okay, so that's the time, and then they kind of monitoring those onset date over the mainland part of India. So the question is like how they make the prediction. And again, this is based on lots of research in 70s. People are actually try to find out the potential predictability of monsoon onset in terms of wind, in terms of pre-monsoon rainfall peak, minimum surface temperature. So there's a lots of study. And based on this study, Pike and Meyer in 2009, they published a study based on that, which are the potential predictors that they can use for the real-time forecast. And this, they come up with that 8 or 9 predictors. And if you look this geographical plot, you can find that all those boxes, they are actually coming with, and obviously it's not the first time they do, like they do lots of trial and error, and at the end they use this thing. And there is a, like, if you look these heat maps of correlation, there is like predictor-predictance relationship. And interesting thing is, like, as those boxes are very nearby and based on some similar kind of atmospheric variable, some cases, so they have their intercorrelation. Or in statistics, we can call it multicollinearity. So that's why they can't just use a linear relationship. They just add a little bit of principal component point on that, so that the predictors can be orthogonal to each other, and then they use a linear regression. So based on that method from 2005, they make the forecast. So as you know, this is a very common thing. Just to mention that as this is in 2 weekly or 2+3 weekly scale, so it's not so easy to predict because it has lots of variability in that and it also have a different kind of impact of those predictors. Not every time those predictors have the same kind of relationship. So it's a very challenging prediction. So here, based on this problem, come up with the idea like, okay, so we're talking about that atmospheric large scale and the small scale variables impact on days, but we're thinking about a linear relationship. So thought like, let's explore a machine learning approach and let's explore some nonlinear regression methods so that we can capture those nonlinear relationship which may be missing in the linear relationship using principal component regression. So that's the whole idea we come up. Now the question is like, try to find out the suitable or explainable machine learning framework, which will be the best. So as we're talking about regression, so obviously we should go for some kind of nonlinear regression using in machine learning. And there is very two popular method. One is decision tree based on regression, and another is neural network. So we started with both the methods, and we try like which will be best and which will be good. So on the decision tree, but before that, I just want to make sure that this is the two method we're talking about today, decision tree and the neural network. So decision tree is the philosophy comes up with different decision and combination of decision. It's kind of yes and no and questioning your idea, and then you come up with one robust decision. The neural network obviously inspired by the biological science, where how the neurons convey their information in nonlinear way. So we all know about those host history. So I'm not talking about this, how they come, but rather talk about a little bit about the philosophy, like how they make the regression. So on the decision tree, there is a two method. One is bagging, which called bootstrapping aggregative, and another is boosting. So this is a part of a research on decision tree. It's not a different. Like people start with bootstrapping aggregation, and then they found there is a lots of overfitting. So they came up with a random forest, because random forest is actually not taking all the algorithm, rather they just take the subset of the features so that they can actually overcome to that overfitting. Then the people come with the idea called sequential modeling. So random forest work like independent, and you have like lots of independent decision, and then at the end you make an averaging on that. But boosting is some kind of you are actually connecting each and every decision in sequential way, so that your decision have all the inputs. So again, in the boosting business, there is a lots of overfitting. So people come with the gradient boosting. And the recent advance in this boosting is called XG boosting, which is actually optimized by gradient boosting algorithm through parallel processing and tree pruning. So that's what like we spend our time to try to understand like which kind of method we should go. But if it is boosting, we should go either gradient boosting or XG boosting. If it is bagging, although like do we go for the traditional bagging or random forest? So again, a little bit of graphical idea like how it works. So in the left hand side, the random forest. So as I said, like it starts with one decision, and then it comes with parallelly all different trees, and at the end you make median or mean and take the final decision. On the XG boosting, you start with the tree and then connect this information to the next tree, and that's the way it goes. So that's kind of decision tree we use here, random forest and XG boosting. In terms of neural network, like again, it's a very famous in art system science. People are using it. But there is a simple network, there's a deep learning network. And the simple thing is like, if you think about your regression framework, it's like you have an input values, or you can think about the predictors. And then you start with the random weights and random bias. And you keep on working with the trial and error method using backpropagation to find it out the best combination. And each and every layer, you have a different function, which actually explain the information from the one layer to next layer. And obviously we have lots of decision based like cost function. So we should think about like, okay, so if we allow this kind of mean absolute error or RMSE, then we can okay with this network way, or you can go back. So that's like kind of main idea. But as we are working with few data sets, because obviously we have like not 100 years of data, we have like 30 or 40 years of data. And again, we have not lots of predictors, we have only 8 and 9. So we have to think about whether we go for a deep learning or simple learning. So you're thinking about like it's best to start with the single hidden layer. So because you should put the multiple hidden layer, and if you have a less number of data set, there's again the problem is overfitting. So that maybe when you train your model, it will be super good, but when you test it, then it will be fail. So we're thinking about, let's start with the single hidden layer feed forward. But when we start with working with that, we found lots of limitation. The limitation is obviously the appropriate tuning of the adjustable parameters, or you can say the hyperparametric problem. Obviously take long computation time because it's it's a back propagation method. So we start with some network, we go back and adjust the weights and bias, and again. So because we're thinking about operational forecast framework, so we can't spend that much of time in terms of operational forecast. And obviously it has like lots of other issue with over tuning. So we from this single layer feed forward, we just go to the little bit of more generalized idea called extreme learning machine, which is proposed by Huang in 2008. So his philosophy is like not every parameter should be tuned. So the way it works, so the first layer, which is between input and hidden, it starts with exactly same with other neural network, like start with the randomized initial weights and bias. But when it gets this combination from hidden layers to output layers, it's work like a linear function, which make it 1,000 times faster. But when you said that linear function, it's not linear regression. They are using that kind of linear function to optimize the weights, and they use a Moore-Persson generalized inverse. It's different than the ordinary least square, because in ordinary least square, it's go with the error minimization, but here they go with the other, like they call G-inverse method. Little bit of equation, like again, because I want to explain like how we choose this method for this regression problem. So if you look like, suppose in our problem x1, x2, xn is the predictors we decided from this PICE paper. And then we start with some random bias and random weights, and it's come up like this kind of linear relationship. But again, this the function is not kind of not using the OLS. They're using they're using some kind of G-inverse, so that it still in the nonlinear essence is there, but we kind of overcome this back propagation so that the network can estimate their coefficient more faster than the general things. So long story short, that we use two different framework. One is neural network based and one is decision tree based. Within decision tree based, we use baking and boosting and see like how they works in real time. So the design of experiment, we use the data from Indian Med Department from 1975 and to 2020. And we use exactly same predictor, same data, the paper they provide, and we open because this PI and others also like the co-author of this ongoing work. So actually they give the same data set they use for the experimental focus, because we try to be like same data set so that there is no influence of any other things rather than the machine learning, because we just want to see like if you replace the principal computer regression with the machine learning, whether we have any skill or not. So maybe in future we can think about adding more parameters, but for this we just fix the parameters as same as IMD. And the way we implement the machine learning, first of all, we have to pre-process, and we just make the pre-process ±1. Then for random forest and XGBoosting, we use a randomized search and grid search for implementing the determine the best combination of the parameters value. For ELM, we try different activation function. We start with the sigmoid, then RBF, and then a linear, different kind of activation function, try to understand which will be the word. And then we run, because this machine learning is always the initial value problem, so we should not run one time. So we run 1,000 times each of the network, and then we make some kind of averaging of these things. And we also run it a level not cross validation because we don't have much data set. We have only 46 years of data set. So we cannot make test and train 20 or 20. Better to use whole the data set, 45 years every time, and keep one out, and then we can fit the things. So that's the way we design this experiment. Next step is like we talk about nonlinear regression, but earlier I just showed the linear correlation between predictors and predictant based on the paper. So before moving to the nonlinear regression, we also have to see the nonlinear correlation, and we calculate the nonlinear correlation based on the Spearman rank correlation. And if you look for each of the predictors, they all have the statistically significant based on the 46 years except the first one. So that's one thing also we have to check, like before going to the nonlinear technique, we also have to check whether they have exist any nonlinear relationship or not. And obviously, based on this thing, we can't use that P1 for these methods. Now, just to show a little bit of results, as this is still our ongoing project, just I want to show some initial results. So based on the data we have from 1975 to 2020 from the dates, we just plot a histogram. And the x-axis are the days since May 1. So when you say the 15, that means May 15, May 20, 25, 30, June comes, and the frequency. So there is some incident we can see. There is an early onset, like 15 May or 20 May. And there is also a late onset, like, because if you think about 38 is like June 1st, and most of the frequency is actually on that 30 to 35 between 1st June to 5th June. But there is still an incident when they have a late onset, which is 15 days apart, like 15 June or 20th June. And our target to capture those extremes, because most of the cases we can actually, because just a climatology, if you just predict the onset using climatology, every time we come up with the 1st June. So let's see how the other models work. So start with the PCR, which is IMD's method. If you look, this histogram shifted in the right. So they still capture some late early onset, but it's like after 25th. That means they're kind of missing those early onset from 15 May. But obviously that frequency doesn't look like the same as the observation. But in terms of the random forest and XGBoosting, they look totally different. Like random forest doesn't capture any early or late onset. It just concentrate about this, 30, 35. Same thing about XGBoosting. It has a very, not like a smooth nature. It has like a break and ups. But if you look at the ELM, which is neural network, it's actually capture most of the distribution compared to observation. Although the frequency is not same, but most of the cases is same. It can capture the early onset as well as the late onset. So that's the first step. We're just looking about the dates in terms of the scale of our methods. Next, we talk about the mean and standard deviation. The mean from the data set, we found 33 because, it's somewhere, some point, it should be 1st June, but the data they provide is come up with the 33, which is 3rd June. Most of the method, they are okay with the capturing this mean. But if you look the interannual variability from the observation is 6. That means there's like 6 days difference, like 6 days standard deviation for each year. And none of the method except extreme learning mission capture standard deviation more than 4. And it's also like, quantified by the that box plot. If you look this box plot in the lower panel, compared to observation to different method, linear to ELM, like except ELM, none of the method actually captured that huge range of the, variability or interquartile range. So that means like this ELM-based neural network actually captured those, variability, which is we are looking for here. Now we go for a little, traditional way to see the scale, and we come up with 2 different ideas. One is index of agreement, which is a ratio of the mean square error. So the root mean square error is like the common way to see the error, but the problem is root mean square error is not bounded. So we can't say like which root mean square error is good or bad. So, but index of agreement is actually bounded between 0 to 1. So anything closer to 1 is better. And Another way we can also like use the Klein-Gupta efficiency, which is a combination of 3 different skill score. What is correlation, bias, and variability? Because we're also looking at the correlation, the variability. So in both the way, if you look the skill maps, the ELM is actually outperform or really good compared to the others. So that's the kind of the result we have up to now, and we're still working on that. And just to conclude and feature scope, because we found some like machine learning framework, but obviously that it should be interpretable and explainable. And we found that in this case, ELM is actually capture the internal variability compared to the other machine learning approach. And right now we are working on like, we are talking about, so up to now we show whatever the observed data set and the relationship between the observed world. That means, those data set we found from the analysis. Now the thing is like, can we predict this thing not in the 15th of the May, rather 15th of the April using the S2S and sub-X models? Because we know like sub-X model or S2S model, they also predict those kind of parameters. So we are working on, first of all, to validate the skill of the sub-X or S2S model, whether they are captured the same way at the observation, and whether they have the same teleconnection like the observation we found. And then we actually replace the predictors from the sub-X or S2S model and using the same machine learning. And we're also thinking about that instead of predicting these things just over Kerala, can we extend to each and every districts or province in India? Because again, the problem is like, if we predict only over Kerala, how about the other part, like northern part of, or the western part, which came much later than the onset of the Kerala? So these are the work going on, and I'll be very happy to get any feedback or comments. Thank you.
Well, thank you so much. Again, a great presentation. And we do have a question for you on the discussion forum. If you can open and yes, this question from Tom Hammer.
Oh, oh, that's a very good question, Tom. Yeah, so it might be, again, we totally don't know. It might be happen that is because of the external learning approach, we, the simplicity or explicitity comes. But that's a good point. I never thought about that way. I will think about that. Thank you.
Yeah, okay, so for others who still have some questions, and we're going to keep this file open for anyone who would like to write a question. We'll follow up with all the speakers and to provide a response later on. So yeah, we've said that, so this ends our webinar, and I just want to say that our next webinar is going to be on December 6th. We have 2 presenters. We have Dongmin Kim from AOML, and also he's going to be talking about EOF modes of Tropical Pacific and Atlantic SST. And also John Gottschalk from the Climate Prediction Center. He's going to be talking about week 2 to 4 excessive heat forecast tools and services. And with that, we finish our webinar, and thank you so much to all our speakers.